it's just a mess. Okay, so one thing useful for, there's another question there, no? No. One thing useful for the Boolean logic, now I'll try and write and or all the time, but you might see this U in my notes. This is the same as or, and this N is the same as and. It's just connected with, it doesn't even matter what it's connected with. Right. So this here is or. Probability that a mobile chosen at random is a Nokia or an iPhone. Is it probability of a Nokia or an iPhone? Now, unless you're getting something out in Thailand or something, can a phone be Nokia and iPhone at the same time? No. Now, I'll put that to you, but most of the time you're just going to blindly say or means add. But maybe in class we'll just say they can't happen at the same time, so or means add. So this is probability of a Nokia plus the probability of an iPhone. Given that you have a random phone, what's the probability of a Nokia?
25%.
Go fish.
Or 45%.
35%. And the probability of an iPhone?
40%.
40%. So altogether, 75%. 0.75. 3/4 of the phones are Nokia or iPhone, so the probability that a random phone is Nokia or iPhone is 0.75. Okay. Next question. Find the probability that a mobile phone chosen at random is defective. How many ways can you get a defective phone here?
3.
3. You can be Samsung and defective, or Nokia and defective, or iPhone and defective. Can any of those two things happen at once? Can you have a phone that is Samsung and defective and Nokia? No. So the or is going to mean and. Sorry, the or is going to mean plus. Right, so here maybe we'll just write down again. So this is or and or. These things can't happen at the same time, so the or means plus. So let's write this down. Probability of Nokia and defective. The or means and. Oh, Jesus Christ. The or means plus. Probability of iPhone and defective. Probability of Samsung and defective. Now, being Nokia and defective, you can get into a whole mess about these, about Nokia and defective, and it should be probability of Nokia by, just make it easy. Probability of Nokia is this, and defective is going to be 0.35 by 0.01. This one is going to be iPhone and defective, 0.4 by 0.02. Samsung and defective, 0.25 by 0.03. If you want to make it harder, anyone want to make it harder?
Yeah, go on.
So probability of Nokia and defective should be probability of Nokia multiplied by probability of defective given that it's a Nokia. And that up there is the probability that it's defective given that it's not. That one there is probability that it's defective given that it's Nokia. So it's just going to be as simple as multiply along the branches. So you're going to have Nokia and defective, 0.25, Jesus, 3.5.
0.25 is something.
Yeah, 3.5, sorry, by 0.1, that's a 3, plus probability iPhone 0.4 and defective 0.02, plus Samsung 0.25 and then defective 0.03. And I should probably put brackets on these. You don't have to, but just to make it a bit easier to see. Now, this we can get exactly right. Now, in this, a lot of the time, you're going to have to make decimal approximations. What I want you to do, if possible, is use 4 significant figures. I get an answer of 0.019. My answer is definitely going to be between 1 and 3%. Why is that?
Because that's the defective.
That's the maximum.
Yeah, the most effective ones as such are the Samsungs, the least effective is the Nokia, so we're going to have some answer between the two of those. Okay? If you have a negative answer somewhere, wrong. Bigger than 1, wrong. Okay. Now the next one is the harder bit. Okay. So a certain mobile is found to be defective, so you know that the mobile is defective. From there, calculate that what's the probability that it's a Nokia. That's not as straightforward as you think, and what you're looking at is you're going to look at that formula we did on the previous page. So we're looking at what's the probability of a Nokia given that we know it's a defective. And using this formula you get, and I'll draw on the picture on the board in a minute, kind of explaining this a little bit more. This is the probability of a Nokia and defective divided by the probability of defective. Now this is the hardest part of the question, although I will say the bottom of this usually will be calculated in the previous part. What's the probability of Nokia and defective? How do we find that?
0.35 by 0.01.
Spot on. Now what's the probability of a defective phone? 0.019. Spot on. And then we can ask the calculator again. Maybe find where it was. Fine. And the answer turns out to be, again, I'm just going to use 4 decimal places here. 4 significant figures, 1842. Now some of the answers that come out here are really hard to understand. This one probably isn't too bad. And I'll show you on the board.
We say this assumption again is it?
Yeah, so this is,
Why isn't an assumption above with the other one? It is.
well, there's only, well, no, there's no assumption here. It's just the only assumption is that it's a phone.
Okay.
Now I'm going to try and explain that. Now sometimes this number can be a bit counterintuitive. Like as I said, where you do, if you do a diagnostic test of a disease, so screening for a disease, and only a small few people have it. When you have that situation, so some examples would be a torch. So you have a battery, a switch, and a bulb. And for the system to work, all 3 must be working. For the torch to work, all 3 must be working. Now what we're going to do is we're going to calculate the probability. If we know the reliability of the battery, I don't seem to we'll just make up a number there. Now, where these probabilities come from is a little bit difficult, so we won't think in terms of the battery running down. We'll just think in terms of brand new torch, brand new battery, brand new switch, brand new bulb. Okay? I'm going to say what's the probability that a battery is defective. I'd say most batteries are pretty sound. We'll just give it 1%. The switch, we'll give it 2%, maybe made somewhere not very good. And the bulb, well, I'm always buying blown bulbs. Let's say that's 4%. And the question is, what is the probability that this works? Now, this one is probably easy enough to use, I think. So what you're going to do is you're going to say, well, you need the battery working. So I'm going to just write the reliability. How do I write this? Just the probability of the system, the reliability of the system. It's going to be handy enough. Maybe we should write this in the notes. So we have the space for it. So so we're looking at this block. Oh, here we got the reliability is 0.9, 0.8, 0.7. So where are we getting this? So this is an old battery. This is a switch that's been used a fair bit, and the bulb, well, the bulb is half knackered as well. Okay? So you need battery to work, switch to work, and the bulb to work. So this, we're going to say this is the battery, the switch, and the bulb. And we have the reliability of each of them. The battery 0.9, the switch 0.8, and the bulb 0.7. And what we're going to look at is the probability that the torch system works. Now this is what you call a series. You need the battery working, and the switch working, and the bulb working. And we're going to assume everything is independent, so and is just going to mean multiply. So I think they nearly are, well, we're going to assume they're independent. There might be some issue with the battery is dodgy, the bulb is in trouble, and this kind of things. But we're just going to assume everything is independent. Okay, so looking for the probability that the torch is working, we need the battery working, and we need the switch working, and we need the bulb working. And we're just going to assume that they're independent, so the and is just going to mean multiply. So probability of the battery times the probability of the switch working by the probability of the bulb working. So we're talking battery works 0.9, switch works 0.8, and bulb works 0.7. Some of the numbers here are kind of taken out of thin air. They're probably better figures. So we get 0.504. It's a very crap torch. Maybe a kind of Kinder Surprise torch. Okay. Now, you have a different scenario then. You can have a slightly different system where you have kind of backups. So one example of a backup you might have, now I'm not actually, someone here might correct me on this, I actually don't know, but you don't want a truck, a big Arctic, to have a pair of tyres at each place. Yeah?
Yeah, double dolly wheels.
Now there's two questions. The first is, why did they do that?
Wait.
Okay, second thing.
One blows.
In theory, if one blows, it won't fit.
Same as using two condoms there.
I don't think that would work. Two forms of contraceptive.
Subtraction.
So in this case, so if this is just that tyre, or this set of tyres, this, we'll just call it this system, there's lots of ways that this can work. You can have tyre 1 and not tyre 2, tyre 2 and not tyre 1,
Tyre 1 won't work out.
or both. Go again there about the tyres.
Tyre 1 won't work out, Tyre 2 does.
I'm hoping it does. I don't actually know, but I think it does. I have a different example here, is where you have two pilots.
For say T there isn't bigger than any one of the units. You would think that there's a 9% chance, an 8% chance, 7% chance.
You need them all to work though.
I know, but you would think that the chances would be greater.
No. So that's probably of them not failing, that's probably them working. So think of, okay, do it another way, right? So you've got a box of 10 batteries, a box of 10 switches, a box of 10 bulbs. In the box of 10 batteries, one of them is faulty. In the switches, 2 of them are faulty, and the bulb, 3 of them are faulty. You take, so you got 1 faulty, 2 faulty, 3. You take a battery, a switch, and a bulb out of that at random and make a torch. Are you likely to, how likely are you for it to get a torch that works? The answer is 1 minus that, about 50%.
Okay, right.
Yeah. So that's why. So the other way is looking at it is, imagine 1,000 torches, right? Now you come up and you've got 1,000 torches. You look at the first torch, or sorry, you look at the battery. 0.9 of them work. 900 out of the 1,000 are fine. 100 don't work. Throw out the 100. So you have 900 working torches. Now look at the switches. Out of the 900, only 80% work. 4 out of 5. So that's about
720.
so let's go 720. So out of the 900, 720 work. Throw out the other 180. You're only down to 720 torches now, and only 0.7 of them actually work. Or 0.7 of the 720 left have a good bulb. So you get down to about 500 torches out of the 1,000 only work. That's where you get a number like that. So this is an AND or a series situation. Again, this is, well, so I know you have all kind of ideas, series resistors. Although actually thinking about resistors here doesn't work too. I tried to do it like that before, it didn't work very well. The other one is a parallel system. So a series system fails if any of them fail. The only way a parallel system is if all of them fail. Okay. So if I'm going for the two pilots on the plane tires or whatever, something like that. Pilot 1, pilot 2, and look, I mean, honestly, two condoms is stupid, but condom and the pill, exactly the same. The only way it's going to fail is if both of them fail. Or, any kind of backup system is a parallel system. The only way it fails is if all of them fails. Now, suppose the probability of a pilot getting very ill is 0.5%, so the probability of them being fine is 99.5. So both of them are 0.995. Okay. Now there's an easy way and a hard way to look at this. So, well, there's a long way and a clever way. So the long way says this works if I have P1 working and him failing, or him working and him failing, or both of them working. 3 R's. That's the hard way of looking at it. Sorry, the long way of looking at it. The clever way is instead calculate the probability of it failing.
Both fail.
Yeah, that can only happen in one way. So look at the probability of it failing. If you know the probability of failing is 10%, what's the probability of it being reliable? 90%. So for parallel systems, you're going to set it up the different way. You're going to say, instead of calculating the probability that it works, you're going to look at the probability that it not works. And of course, the probability that, well, we'll write this, this is a little bit confusing, but what you have is the probability of it not working. So the F here is, it's reliable. So this is the probability of the flight. So the probability of not having a flight, in other words, the probability of failure, probability that both pilots die, is 1 minus the probability that the flight goes as planned. So if you know the probability of, basically it's just saying if you know the probability that it fails, it's very easy to calculate the probability that it succeeds. There's no real point writing that, I think. So what instead you should ask is, what is the probability of it failing? So the probability of it failing, and I'll actually write failing as this is flight, it's a little bit confusing. So the probability of the flight failing, so I'll write it 2 different ways, maybe write not a flight, or easier, probability of failing. You need pilot 1 to fail and pilot 2 to fail. That's the only way that this happens. P1 fail and P2 fail. Now again, we're getting into dangerous water here. I mean, we said the and means multiply. That's if they're independent.
Where was that P failed?
Sorry, that should be P1 failed, pilot 1 failed, and pilot 2 failed. That's this much. So I said and means multiply. This, you're getting into kind of dodgy water. I mean, if the first tire blows, does that make it more likely that the second blows at the same time? It probably actually does.
One way, huh?
Well, it's at the same time, I'd say. I mean, what causes the first tire to blow? Maybe the glass could be there. They're actually not independent, but just throw that all out. And means multiply. Okay? Just make some of these a little bit off. Like for the pilots, if the one pilot goes kaput, now probably it's only a smaller increased percentage the second. I mean, it could be poisonous gas or something like that. But yeah, look, they're negligible. Just forget about them. So the and means multiply. Probability that pilot 1 fails times the probability that pilot 2 fails. Now 99.5% of the time there are no issues whatsoever with the pilot.